What's going on, everybody? Welcome to CS540 Week 4 Keel Climbing. So if you're new here, welcome. Be sure to check nearlyblog.com and click this image and you're able to find this page. So in this week, we are mainly talk about three important concepts which is crucial to neural network. One is hill climbing, second is simulated annealing, third is genetic algorithm. Though these three terms are not the official names for neural network, but the concepts are basically the same. And since this week is mainly about the concepts, there is no Python coding part, and I would like to relate all these concepts to neural network, so you guys can have deeper understanding about what them really are. So first of all, I would like to introduce briefly about neural network. So neural networks is kind of deep learning, and deep learning is part of machine learning. So for neural network, it's just like the brain, the neurons in our human brains is just the similar architecture. So every time we will have a input, and we call that X, and every circle like this is actually a neuron, and there are many neurons laid out in one layer, and we call it layer 1, for example. And every time just fully connected. Later I will demonstrate what's the algorithm inside, and it might have a lot of layers, and each of them will just fully connected. So every previous node will connect with all the nodes in the next layer, and it might have a lot of layers, and in the end it will go to here is layer 1, here's layer 2, blah blah blah, and this is layer n, and here's the output layer, and we usually don't put L output or something, we just put output layer. And the output layer can, for example, either output the unbinary case, and we call that sigmoid function. So sigmoid function will only output 0 or 1. So this case is, for example, I want to recognize the image. For example, I just want to recognize whether the image is cat or dog. So probably 0 is cat and 1 is dog. Then I can just recognize it. And there is another function called softmax function. So it can be from 0 to, for example, if it use VGG16 neural network model, then it will have 1,000 different options, and it actually starting from 1 for VGG16 specifically. So this kind of so this is actually the activation function, and later I will show you the hill climbing is actually also one kind of activation function, which is really important. So they can for softmax activation function, it can output 1,000 different outputs, which is to say I can recognize 1,000 different objects. So here, first of all, I would also have brief introduction about the algorithm in the neuron. So let's just, for example, take from, let's say this is node A, neuron A. So I just have a demonstration from the beginning, the input X to A, and what's going on here. So let's say there is an input X, and there is actually a weight here, so which is before the neuron, and there is also a bias added to the neuron. So what the algorithm do is first it calculates a z. So z equals to x times w and plus b. So this is just a simple calculation here. But next is what really the activation function works. So here, for example, I have a activation function that is sigma. So the activation function will just do something with the z and get an output. So let's say output y equals to sigma function of z. So this is how it works, and it will just output an output y. So let's take a look on how hill climbing works. So what actually basically hill climbing says is just it will just find, it's really greedy. It will just find the best solution. And actually in this case, it is what we call a unit function. So let's say here is fn, here is n. So when n is smaller than 0, then fn is just 0. And in other cases, when n equals or greater than 0, then fn is 1. And here is the same case. So if z is actually greater or equal than 0, then the output will just be 1. If z is smaller than 0, then the output will be 0. However, this kind of methods is really doesn't make sense in neural network. And the reason why it's like this is because it always output as something, and there is actually no slope. The slope is the derivative change. So actually neural network, the reason why it will train these two parameters here, and of course also other parameters, that's weight and bias, is because it really has the slope change of we call the loss function. So loss function is the function that measures the error of the whole neural network, and for one simple connection from, for example, from x to this node. And we also have a cost function that is the whole error of the neural network. So what we actually do in neural network is we just take the derivative of cost function and times we call it a learning rate, and do the changes with both the weight and the bias, and just to tune these two parameters in order to make our neural network perfect. So here is a brief introduction about hill climbing. So how about simulated annealing? Let's take a look about that. So here is in PowerPoint from our lecture notes. So what the simulated annealing actually does is, it's just like here it says the Boltzmann distribution. So unlike the hill climbing just to output 0, 1, it actually do some changes. So here just now we talk about the neuron and also the activation function. So here is an input and here's a neuron. Then you have an output y. Here's a weight and also a bias. So here the sum, we can first calculate the z here, that is x times w plus b. Just one thing I would like to mention here, here both x, w and b is actually not just one integer, it's kind of matrix. So those matrices are just, for example, the x, if your input is actually image, you are going to transfer x. If you're using RGB format, then you have a 3-dimension matrix. So here, unlike last time, we will have a function. So there are two actually functions really popular, and I believe in simulated annealing function is actually called the sigmoid function. So So it's actually 1 divided by 1 plus e, if we say it's n here, minus n. So the graph is actually like this. So when the n is 0, then this point is 0.5. And when n is extremely large, then it converges to 1. And if n is extremely small, then this part will just converge to 0. So in this case, all the outputs will be in the range of 0 to 1. So y will be in this range. So the advantage compared to last time, you remember the unit function, is actually because every slope here, every point here got a different slope. If it's really in the middle, then the slope is pretty large. Not pretty large, just larger compared to the other two sides. If when, for example, when n increase or decrease, the slope will actually gradually decrease to 0, and this is the beauty of the this kind of function compared to just the unit step function. And another thing I want to say is there is also another very popular function that we call the tensor function. So tensor function is actually some changes from sigmoid function, then you just put -1. So here the graph is like this, and both of them converges to either 1 or -1, and when n is 0, then it's just 0. So these are just mainly two activation functions. So we talk about the simulated annealing concept, which is just to change the activation function from our hill climbing, which is the unit function, to other kind of functions which have different slope. But how about generic algorithm, and what is function of generic algorithm does? Let's take a look. So what does generic algorithm really talks about is it says, okay, for example, the parents, if they are going to have a child, then the child DNA is actually randomly selected from either his dad or mom's DNA. So in this case, I will relate this part to actually the update of the bias and weight part. So what does this mean? So just now we talked about Z equals to X plus B, and we use our A here to get the output from, for example, the first node after the activation function. And here we just use the sigmoid function, and we are able to calculate these which is using calculus. I just skip this part, and also we are able to calculate dW, that is the slope of the weight at that point, and also we have dB. And next, what we're going to do is in neural network we actually have forward propagation, and also we have backward propagation. So forward propagation is just these two parts. So it's just to calculate. And in backwards calculation of propagation is it calculates all the derivatives of these parameters. So after a forward propagation and backward propagation, that is we call one epoch during the training. And actually after each epoch, we are going to update our parameters. So here, in order to update the parameters, we have our W and B get changed. So W, the weight will just equals to this one, and alpha here is actually just the learning rate. So now we talk about the learning rate. Why learning rate is so important? So if you can imagine, here is a bow. Just here is a bow, and here is a ball. So just imagine it's in a probably I just draw like this. So just imagine it's a 3D one. So what you are going to do is you just find the minimum loss. That is the local minimum point, and that is exactly what talk about in the hill climbing. It says it wants to reach the maximum, the global maximum point instead of the local one. So here I just do the reversely. I want to find the minimum loss here. So I just want to go down. So this is and here is a bow, like it's a curve. Every time when it goes down and down, especially at the bottom, the slope is actually 0. So actually we just want to find this. But what about the local minimum case, which is here? If we just stop here and stop directly, then you will just stop at the local maximum point in this case, which is local optimum point. You are unable to reach the global optimum point. So this is why we have the alpha here. And actually, sometimes we also have momentum, but here just want to make it simplified. So like after it reaches, just like in our real case, you have the gravity, so it will just increase a little bit, then come back, then come back. So it's like this, from here goes to here, and a little up a little bit, then go down a little bit. So it might help that. So for example, in this case, it won't stop. It will just continue funding until you find another point, and the alpha will actually get updated all the time. So here I would like to show you something. So in the lecture notes, it actually say that so P here is actually 0.1, and the P here is just the possibility, and this is the reason. So usually, for example, if you use TensorFlow Keras API, it will initialize your learning rate to 0.1, and this is exactly the thing why we want to put it as 0.1 here, which is get updated. So you see here, else t is worse than this one, then it will accept this, but it will just accept it with time 0.1. And the second reason is why p decreases with time. So in TensorFlow Keras, we actually have reduced learning rate amplitude, and what does that do is every time after one epoch, you remember that graph. Every time after epoch, you are going to reduce your learning rate, and the reason is we really don't want the ball rebounds out of the ball. So when p decreases with the time, also with the boundness, this is will increase, and that is true. So I know it's a little bit hard for you to understand if you do not have some basic understanding about neural network, but I do hope and I do think this is the better way to really like associate these concepts with the neural network. So I know you guys might have some concerns or questions. So whatever question you have, just leave comments below. I'll try my best to support you. Thank you very much for watching, and hope to see you in the next week tutorial.